So, welcome to Functional C++ for Fun and Profit. Thanks everyone for coming. Nice to see a packed room. I'm hoping not going to be a tough crowd. But I'm Phil Nash, my Twitter handle there. I recently changed my job, so I'm now a developer advocate at JetBrains. It's the t-shirt as well. So this is interesting because I've been doing conference talks for years now. And previously I've never really been able to put my company name up there because it's never been particularly relevant. Worked for a bank. It's not that I was ashamed of it, just wasn't relevant to what I was talking about. So now, of course, I'm putting the company name up there. But most of the material I'm going to talk about today is actually based on what I was doing in my previous role. So finally, I get to talk about it. So that's really why I chose the title for Fun and Profit. I want to try and emphasize that this is real-world application of these techniques, things that I've actually used to good effect in this previous role. Obviously, I can't use any of the specific code that I was working on then because that's all proprietary and I don't have access to it anyway. So in some cases, I've just recreated some toy examples based on that. But do be assured, this is based on stuff I've actually used in real code. So you may also know me from my test framework, Catch. I know quite a few people here use that. And at JetBrains, I'm representing the free C++ based tools, C-Line, AppCode, and ReSharper C++. Not really going to be talking about that here today, but obviously you can catch us at the booth downstairs. Ask us many questions you like there. So we're going to talk about functional C++. As I said, it's based on real-world practical code. I'm going to try and steer away from the purely academic stuff. Not because that's bad or wrong. You'll find that plenty of other places. It's not for everyone. I want to keep it focused and practical. But I do want to start by actually defining what functional programming actually is, because it may not be what you expect. Just for a moment, close your eyes and imagine you're not seeing this slide here, and just think to yourself what you think functional programming actually means. And you might be thinking of things like first-class functions, higher-order functions, immutability, referential transparency, monads, any of those sort of things. You can open your eyes now. They're definitely all important parts of this sort of tag cloud around functional programming. And we'll definitely be looking at most of those things today. But that's not really the root of it, that everything else hangs off. So I've got this quote up here from the Haskell wiki, definitely one of the authorities on functional programming. I just want to highlight that very first sentence. It says that functional programming is a style of programming which models computations as the evaluation of expressions. And then just a bit further down the same page, it goes on to say, in functional programming, programs are executed by, again, evaluating expressions, in contrast with imperative programming, where programs are composed of statements which change global state when executed. Functional programming typically avoids using immutable state. So it's a few interesting things there. First of all, that idea about it being evaluating expressions. As we'll see, this sort of leads on to using first-class functions and all the other things that we mentioned. But it particularly contrasts it in imperative programming with using statements. These two things are sort of described as being in opposition there. It also talks about how that leads to using mutable state. And particularly interesting, at the end it says functional programming typically avoids using mutable state. It doesn't say always, it says typically. That's sort of the focus. So we're going to unpack all of that, I think, as we go through this material. But I first want to dig into what it really means to be expression-oriented in this way that it talks about. So I'm going to use a very simple example from some typical C++ you might see in any code base. You've probably written this sort of thing yourself. Start off with some variable, and we just want to give it a value based on a condition. So we use an if statement. So here's a statement. And there's a lot of problems with this code. It might seem small, trivial problems, but there are problems there. And I'm going to argue that they're all caused by the fact that we're using a statement here. So let's have a look at this a bit. So inside the if statement, within the scope, we have these values, the yellow and white colours. We want to initialize that variable with them, but the only way we can get them outside of that scope is by using assignment. In other words, a side effect, which requires mutable state. So here that mutability comes into it already. Introduce a side effect. Plus, we've had to start off with an uninitialized variable. Now, we could give it a default value. That may not be what we want. It may just be swapping one problem for another. And we can't make that variable const because we needed immutability, even if after this point, we never need to change it again. And that affects the way you can reason about the code. Because if you imagine this is part of a long function that constantly refers back to color, in order to know what the value might be, you have to look at all the other points in that function to see what things might be mutating it. If it was const, we wouldn't have to do that. Now, we're probably a little bit used to ignoring that, because in C++, mutability is the default. Most of us don't write const everywhere. Some of us do have that discipline, but for the most part, it doesn't seem to be worth it. But if we did want to make it const, we can't, because that statement is stopping us from doing it. So quite a few problems for such a small piece of code. And these problems tend to multiply as the code scales out. And we just got very used to just sweeping them under the carpet and ignoring them, but they're still there. They still bite us. So what would this look like if C++ were actually expression-oriented? So just theoretically for a moment, imagine that C++ was expression-oriented and had if expressions. It would look something like this. So now we open the if, and each branch of this if statement evaluates to a value. We haven't had to use assignment. It does mean that we need both branches. We can't have an if without an else, because we're going to evaluate the whole if statement as an expression into a value, and then we can use that value to initialize our variable. So now we can make it const, no mutability, and as a bonus, we can use type inference as well. And all these things often tend to come together, just making that little change to using an expression. And in fact, if we look at an example from another language, I like to use F#, so that's the example I'm going to use here. You can see, apart from a little bit of syntactic difference, it's basically the same thing. This is how we write things in a real functional language. But of course, C++ is not like that. We can't do that in C++. And at this point, of course, you're all screaming at me in your head, saying, yes, we can do that. You can use the ternary operator. And yes, of course, we can do that. So this actually has all of the same properties we just described that we wanted. We've got the immutability, we've got the type inference, we've got no side effects, and we've got that property of local reasoning, because that value can only have that initial value, and it can't change throughout the rest of the function. So what's wrong with that? Not that much, actually. Now, we're usually advised to be very careful about using the ternary operator, maybe banning it altogether. Has some readability issues, and there's some truth in that. We do have to be careful with precedents, and we don't want to make the branches too complex. And we certainly wouldn't want to nest these expressions. That definitely can have problems. But for simple things like this, I actually advise using this for exactly the reasons we just described. Has all those desirable properties. It just solves that problem. Now, the biggest problem with this, it's just not general enough. It doesn't really scale out. So if we had more cases, then we'll have to resort to a switch statement. So here's basically the same pattern again, but now we're using 3 cases. So we could do that with the ternary operator by nesting things, but like I said, I wouldn't advise that. So we seem to be back in the same situation, but there is one other way that we can let those values escape out of the statement. Ironically enough, introducing another statement. The return statement. If we shift that code into a lambda, then we can return out of it and initialize our variable again. Back to all the same properties, we just introduce a little bit, or another concept into the code. You might be thinking that seems like a case of using a sledgehammer to crack a nut, all this extra syntax, all this extra code, but actually is it? think about it for a moment. This is actually less code than the example with mutability, mostly because we got rid of the break statements. But it's actually 10 characters less in this example. So that's nice. Not necessarily a motivating factor, but it certainly shouldn't stop you. But maybe it's less efficient. You know, we're introducing an extra function call here, passing variables in. It's got to be a runtime cost. I'd expect any decent compiler to optimize that away. In fact, it's not just an expectation. I ran this through the Visual C++ compiler, looked at the assembler, compared it, and it was pretty much identical. Zero cost to this particular abstraction, at least in this case. So I wouldn't avoid it for that reason either. So it might look a bit unnatural at first to do things this way, but give it a try. See how it feels, maybe write more of this, and start to appreciate the benefits of using expressions instead of statements, where you can, where it makes sense. Doesn't always make sense, but where you can. So that's if statements, and switch statements, and return statements. What about loops? They're also forms of statements. They have all the same problems that we just talked about. There are other ways to deal with loops. We can use standard algorithms, for example. Standard for each doesn't really solve the problem. It's just doing it a different way. Usually what you want to do is use something more specialized. If you're transforming, use transform. If you're accumulating, use accumulate. Now, these are all examples of higher order functions. So where this comes in now. So a higher order function is simply a function that takes another function, or lambda, as one of its arguments, and or returns a function, or a lambda. And there's actually quite a few examples of those in the standard library. We've got all these if and if not variants as well. The top three are of particular note because they map onto concepts that you'll encounter a lot in the functional world. Transform is the same as map. Copy if is like a filter. And accumulate is an odd one. It sort of maps onto reduce, depending on the definition you use. You might say left fold as well. But it's not in the algorithm header, if you're looking there for it. It's in the math header, presumably because it's originally intended to be used on numeric types, but works with any type, any value type, really. So they're interesting. Use those where you can. They're a lot better now. We have lambdas. There are still some limitations with these, though, that make them not really suitable for functional programming. And we'll come back to that maybe a bit more towards the end. So I'm going to move on to another topic for a moment. And this is really expanding a bit more on the concept of immutability. We talked a little bit about why it was desirable to use immutability because we can reason about the code more easily. You hear this a lot in functional programming circles. It's all about the reasonability of the code. Applying local reasoning, I mean, you don't have to look at all the other parts of the code to understand this bit. You can just reason about that bit alone. Immutability is a really big factor in that. And this is something that I call the builder pattern. I say I call it that. Doesn't mean I coined the term. I just don't think there's a universally agreed on name for this. If you know any different, do let me know. But I've seen other people call it this. I call it this. It makes a lot of sense. It is very different to, or it is somewhat different to factory methods. Not polymorphic for a start, and has a different purpose. So let's have a look at what I'm talking about here. If you're separating functions from data, which is what you typically do in a functional programming language, it's sort of the opposite direction to OO, where we're trying to move them together. You tend to end up with these sort of plain data types with just the data in there. And because we want to write immutable types, we're making all the members const. We want to try and make them transitively const, which C++ doesn't do for you, so you have to write, if you've got pointers to things, you have to make the thing pointed to const as well, and then use immutable types there. We can deal with all that, it's a bit of a pain. But this is now really safe to use, because once we start using it, we know that nothing can change it. So it's not going to have any setters. So a lot of the usual reasons for encapsulation just disappear, because once we've constructed something in a valid state, it's going to stay valid. which is why this gets used a lot more in functional programming rather than objects with methods that mutate things. Notice I deleted the default constructor there because it's not usually appropriate to construct these in a default state because you can't then put any values in. In this case, it was unnecessary because that's implied by the fact that we've got constants and constables, but I think it's worth putting in there anyway just for documentation purposes. So how do you construct these in? Notice I haven't got any constructors there at all. Well, nice feature of using these plain data types is we're then free to use the member-wise initializer. So we can construct these directly like this. And in a way, the layout of the class becomes its own constructor that way. Again, it's much nicer to do that when there's all this other noise of other methods going on. But this is not always enough. Because in real-world code, things get messy. It can actually be quite complex or complicated to gather all the bits of data that you need in order to construct something, particularly when we talk about domain types. I said these are sort of proxies for stuff that I worked on, which was mostly like financial objects in the quant library. Some of these objects take 10, 20, even 30 arguments to construct. You have to gather from all over the place. You often have to wait for asynchronous things to come back before you can construct them. So I've tried to sort of mirror a little bit of complexity up there. Tends to involve using all these extra local variables to gather that state together before we're in a position to construct things. And that's fine, you can do that. Do that a lot and it tends to feel a bit awkward. You start thinking, well, if this type was not immutable, if I relaxed on that a bit, I could just construct it as I went and it would be so much easier. Well, don't throw the baby out with the bathwater. What we can do is just have a parallel type that I call a builder, hence the builder pattern. So it has essentially the same fields. They may or may not be different types, depending on what's appropriate. You can do what you like here. This is just for a construction phase. So these are not const, they are mutable. Typically, if they've got pointers in there, they'll still be pointing to const things, so you'll use constructors for those. But you can build these types up as you go. And then when you are ready, when you've got a fully valid type, you can call a build method. There's other ways to do it, but I like this way. Call a build method that then gives you that object in the representation that you would like. In this case, it's in a shared pointer. It could be a value. Notice in there we are using the member-wise initializer. Now, why would you do this? Because didn't we say that we wanted immutability? And now we're deliberately making this mutable. The idea here is to control the scope of the immutability. So where that's convenient, you can still use it while still getting the benefit of having immutable domain types for most of the time. So in use, it's going to look something like this. It's still sort of drowned out by that other complexity, but notice now we're building it up as we go. And instead of the constructor at the end, we just have build. Doesn't seem to save a lot. Does add up though. But you start to get more of a win when you introduce things like asynchronicity. So let's imagine that that contacts book had an await method on there. Just highlight that there. So maybe it's going to go off to a database, and then it's going to call you back on a Lambda when it's got that data back. So the Lambda here, assuming C++ 14, generalized Lambda capture syntax, means that we can actually move our builder type into the Lambda. So if you don't have C++ 14, you have to copy it in. If you can move it in, it's really nice and efficient. So normally you would want to keep these builders in a very limited scope. But if you can move them around, then that's okay too. So that makes it really nice and convenient, because if we had a load of local variables and we needed to move those in, it's going to be a lot more code in that move in the Lambda capture. So once that's in there, you can carry on building it, and when it's complete, obviously it's up to you how you use it. That's difficult to really convey the benefit of this in a simple toy example in a few slides. We use this for hundreds of domain objects, and it's really made it much easier to reason about what we're doing without losing the conveniences of mutability. And when we talk about functional C++, we've already established that C++ is not a functional language. It's not expression-oriented. There's a lot of things you can't do or it's really awkward to do. And functional C++ is really about taking the best parts of functional programming that we can actually use and marrying them with the best parts of C++. And where C++ really shines is in that sort of low-level, we're fiddling with little bits of mutability. If we can keep the benefits of that while also having the reasonability benefits of functional approaches, then we're winning, I think. That's what I want to try and get across here. So, a little aside, this will come back to builders again in a moment. I want to talk about a fast and safe ref-counted string. Now, what's this got to do with functional programming? We'll get to that. But this may remind you that standard string was originally designed, so it said, to allow for reference-counted implementations. And many early implementations were ref-counted, some up until quite recently. GCC only recently switched. So when you have a ref-counted implementation of something that has a mutable interface, which standard string does, that typically implies a particular technique called copy on write, often abbreviated to CAL, which makes for nice visuals. And that's the technique that was typically employed. I'm not going to go into too much detail because I'm sure you're all familiar with how this works. I just want to recap briefly just to get a baseline. So the idea being you've got strings that are copied, they're sharing the same data, so they're actually pointing to a single buffer with a ref count. But as soon as you invoke some sort of mutable operation, then it needs to take a copy of that buffer and it can mutate that now that it's unshared, which all sounds well and good. There's a few problems. First of all, what counts as a mutable operation? It's often just accessing an individual character in a string. If you're not using a const string, that's a mutable operation. And there are some workarounds for that, but it may often be copying things unnecessarily. Bigger problems are because although you may only use individual strings on separate threads, the shared buffer may be shared across threads, so you need locks or atomicity internally as well. So that ref count at least needs to be atomic. And with all that possibly unnecessary copying going on, there's a lot of checks on that, which means a lot of those atomic variables being loaded. That can cause a bit of a performance hit. And that was one of the main reasons that some of the early implementations switched. I think that was the reasoning behind the Visual C++'s switch. Another problem is that because that mutability is going on unseen to you behind the scenes, it's unpredictable. And it can lead to dangling references and iterators non-deterministically. And that was actually allowed by the original version of the standard, even though it was undefined behavior, not very desirable. But that gap was plugged in C++11. So as of C++11, it's no longer possible to write a standards-conforming standard string using copy on write. Technically it is, but you would lose all the benefits, so nobody does that. And that was in fact why GCC more recently switched. So bottom line is that cow runs like a dog. So as far as I know, no standard string implementations now use copy and write. As I say, what does this have to do with functional programming? Well, first of all, it would be nice if we could share data because immutable types typically involve a lot more copying than you might normally want. So we want to make that efficient. And it turns out that if you start with an immutable design, then all those problems, almost all those problems, just magically disappear. So if you have an immutable string type that you can fairly easily write yourself, then we start off with that same situation. We've got our strings that are copies of each other, sharing the underlying buffer, got a reference count, and that's it. We don't have that copy and write step. Although all the problems associated with that go away because we've taken away the mutability. And this is the common theme of functional programming, is that by introducing constraints to the way we can do things, a lot of problems associated with going outside of those constraints go away. So it might seem like we're making problems for ourselves. We're actually solving those problems. We don't even have to think about it anymore. And that's true here. But there's a reason that standard string does have immutable interface, because sometimes you do actually want to mutate strings, whether it's building them up in the first place or having got a string mutating it later. Can we do that with this? Well, it turns out we can not only do it, but we can do it better than the copy and write version. First of all, in our implementation, we have things called string refs, which are very similar to what in C++17 we've called string view. So simply a very, very lightweight type that has a pointer to the start or a position in the string and a size. And these are non-owning strings. And oftentimes that's all you need. You can slice this string up without ever needing to take a copy very efficiently. And the nice thing about these is it also works across types. So you can have a string ref into one of these immutable strings and another string ref into a standard string, and you won't actually know where they've come from. You don't need to. So that's nice. And as I say, you can do that in C++17 out of the box. But for when you actually need to mutate strings, going back to the builder pattern, we introduce a string builder to control the scope of the times you do actually need to use mutability. And because that's the purpose of this type, the interface is optimized for mutability. You can get buffers that you can pass out to external libraries to populate. You've got all the mutable interfaces for individual characters. You can truncate strings. You can realloc and create longer versions. That's all fine, because this is only to be used in the construction phase. And you know exactly what you're getting. You're never going to have iterators into these. It doesn't even have an iterator interface. But once you're done building up a string, usually very quickly, then you're ready to get a string out of it. You could take a copy, but that would seem wasteful. So internally, the string builder has that same reference count, not publicly accessible. It's always fixed to 1, so it's never shared, so it's safe. But then you can construct an immutable string from that and detach or move it. I say detach because when I wrote my version of this, it was pre-C++11, didn't have move semantics yet. So detach did the same thing a little bit more explicitly. You can use either approach or both. I went back and added standard move to my one. So now you just move that storage into the standard string. String builder no longer owns it. The string does. Because the string is immutable, you can now freely share that, just like you could before. So we've got no loss of efficiency there. But then later, you may want to start mutating it again. So again, you can standard move that into a string builder. And if it is shared as an immutable string, then it will take a copy. So just like with copy and write, we need to consult that reference count. But now this is the only place we need to do it. Only place that we need to check whether that string is shared or not, other than, of course, the destructor. So we've almost completely solved that particular problem as well. I made it very explicit where that mutability comes in. And of course, if the string is unshared, then we can actually safely move the buffer in to the string builder and potentially move between mutable and immutable states without any copies at all. So just to summarize that, typical lifetime might be we'll start off with a string builder. Again, we're very strictly controlling where that mutability can take place. Take advantage of that low-level control that C++ gives us to very efficiently build up a string that we can then treat immutably for most of the rest of the program. And if we need to, we can still take mutable copies later, which again may not even take a copy. And then we can freely share things about. So like I say, all the benefits of copy and write, but with almost none of the downsides, and a load of additional benefits too, because now we can reason about those immutable types much more easily. Now, it's not just theoretical. As I say, we had our own implementation of this, and I was pretty convinced that it was performing really well, but I didn't want to leave that to theory, so I did run a test where I set up some real-world test case that was going to run over a long period of time using real data and took some performance metrics. And then I made some changes to our immutable string, so it actually worked very similarly to standard string typically does now, with no reference counting, small string optimization. Ran those tests again to compare, and I found that the reference counted immutable string performed significantly better. Unfortunately, I don't have those figures to share with you. I don't remember them off the top of my head, but I'm guessing something like a 20 to 30% total improvement in the speed of the application. Quite significant. So you get both a performance benefit and a code reasonability benefit. So what's not to like? So that's just another example of using the builder pattern. Now, strings are really just special cases of arrays. They're just arrays of characters. So of course you can apply the same approaches to arrays, and we did. We had array builders, mutable arrays, array views. But arrays have some slightly different characteristics that meant that wasn't always so appropriate. They often are much bigger, so the cost of copying when you do need to is much more expensive, and you do tend to mutate them in place a lot more. So we had a few variations on that, and we often just use standard vector. But that's for linear data. But there are some other approaches you can use, and we may touch on that a bit later. The more interesting case, though, is when you have more of a node type of structure. We can borrow a technique from the functional programming world called persistent data structures. Now, just to clarify, the persistence here is not talking about databases or files. This is about making new versions of something based on an old version and keeping the old version around, persisting the old version, if you like. For as long as you need it, then you can throw it away. And it's mostly about efficiently sharing as much as possible in what's common between the new version and the old version. To illustrate what I mean, we use the simplest possible example, which is a singly linked list. So again, I'm sure you're fairly familiar with how singly linked lists work. So just very briefly recap. Each node in the list just has a pointer to the next node. So the first one's usually called the head, and the rest is the tail. Very important that the links don't go back the other way. And the reason is because, first of all, you usually have some sort of wrapper type that has that initial pointer and often a size that you can then access in constant time. But if you want to add something to this list, rather than mutating it in place, you actually only need a new head pointing to the head of the original list. So then you have two lists, but almost all of it is shared. It's a very efficient way to represent things. And of course, you can use the same process for removing items and doing other sorts of operations. All the time you're working at the head of the list, these are very efficient operations. And you can actually keep previous generations of this structure around with almost no cost, which can actually be really nice for concurrency in particular, as well as reasoning about your code. The concurrency angle does need a little extra spin because we need to be able to do atomic swaps on these initial pointers. I'm not going to go into that too much here, but it means that you can construct a whole new list, or whatever the structure is, and stick it in some globally accessible location, and have that instantly seen by other threads. You need to do a copy and swap, because if someone else has done the same thing at the same time, you're going to need to redo the operations again. So it's a type of optimistic locking. Haven't really got time to get too much into that, because there are some problems with linked lists. They're very popular in functional languages because of this property. They don't tend to suit C++ applications very well because with all the pointer hopping, they're not particularly efficient, particularly because of cache locality. And the other problem is if you ever need to do stuff further down, particularly towards the end of the list, then all that copying overhead comes in. You generally have to structure your code in such a way that you're mostly working at the head. But it's good for illustrative purposes. So, more interesting are tree-based structures. Again, just very briefly, it's a very simple binary tree. Now has two pointers instead of one, usually called left and right. And these typically model associative data structures. So standard set, standard map have these. So there's an ordering imposed from left to right, usually by some key value. So if we want to introduce a new node, then we need to find its position in that list by doing a binary chop. And we typically have a choice of where to put it, whether we want to associate it with the left or the right side. But when we do that, we have to write a pointer into its parent. So that involves a mutation. So if we want to make this persistent, then we're going to need to make a copy of that parent node and write the new pointer into there. But once we've done that, we now need to write a new pointer into its parent node and so on up to the root. So this mutation actually ripples up to the root. But the benefit you get from that is you've now got two trees. We've got the original tree in its entirety still there, and then the new tree with the new nodes down one side, but most of the rest of it is shared. So a larger tree would actually share a lot more, have a lot more in common with these nodes. And you will just typically get this sort of linear mutable ripple up. So it sounds like a lot of copying. There are some ways to mitigate this I'll talk about in a moment. But there's another problem with this, the naive approach. The depths of these branches can get very inconsistent. In fact, the worst cases are really bad, and they're really easy to get into. If you just load one of these trees up with already sorted data, then they'll all be down the left-hand side or the right-hand side, and they'll just be like a linked list. So we're back to that problem. So typically we have an approach that will balance the branches. Remember I said you've got alternate positions you can put things in. I'm not going to go into the nuts and bolts of it, but you've no doubt heard of red-black trees. I'm sure some of you are familiar with how they're implemented. It's just a couple of simple rules that you need to apply locally to a little cluster, and then the tree effectively rebalances itself. Does mean that you get a little bit more copying going on because of changing a few more nodes. I'm actually screwed up a bit because I drew up this example and then realized that to make this a red-black tree, properly balanced, I didn't actually need to change anything. So I can't illustrate how that might change, but that is a valid red-black tree. So I said there were ways to mitigate that copying. And ironically, it actually involves copy and write. So the idea is that our left and right pointers, we make them shared pointers. Now in our implementation, we had our own intrusive pointer because it's much easier to do it that way ourselves. But nowadays you can atomically swap shared pointers as well. So that's the property we needed. If you make these shared pointers, then we can tell whether a particular node is shared or not. A little bit more to it because this node here, for example, may have a shared count of 1, but the root node might be shared. So as you go down the trees, you traverse down to find the place that you need to get to. You check each node's sharedness, and the first time you hit a shared one, then the rest of the branch is shared. So you can do that actually fairly efficiently. Sounds like a lot of extra bookkeeping, but it's not. So any nodes that are not shared, you can actually mutate those in place. And that's actually safe to do because until you've rippled all the way back up to the top, no one else can actually see the results of that mutability yet. So you can use mutability internally as long as the eventual new root that you give back to the caller, from that point on, it's not going to change. So that's a really nice way to efficiently deal with not doing too many extra copies. And what we found in our use case was that the extra copying had typically around about 10% overhead over a purely mutable set, which was actually really good considering all the benefits we got from it. Not just in terms of being able to reason about the code, but particularly that concurrency. We didn't have to do anything else almost to make this concurrency safe. Just out of the box, it just worked. And we had additional advantages as well. In our use case in financial data, we often needed to run scenarios where we'd have whole object graphs of data. We wanted to change a variable and then have a new object graph that had all these mutations. And this allowed us to efficiently share those different versions of the graph and keep them all in memory, which we couldn't do before when we had an immutable set. So that was really useful. It's actually not the most efficient way to achieve an associative data structure. Probably a better structure you could use, and I don't have a slide for it here because I didn't actually implement one yet. Something called a persistent hash tree. And that's tree spelt T-R-I-E. Some people call it a trie. And this is sort of like the marrying between a tree-based structure like this and something more like a hash map or a hash set. And it's just a way of dividing the hash code up into smaller chunks, usually 4 or 5 bits, and you use that as your key in the node, so you very quickly get to your branch depth, where you then do a linear search like in a hash map. There's a little bit more to it. You can look it up somewhere. The key point is it's actually easier than a red-black tree to make persistent, because you don't have the rebalancing step, so it's actually more efficient from that point of view as well. So if you do want to use something like this, have a look at that. I'm going to have some references at the end, by the way, and one of them is the blog site of Bartosz Milewski. He has a series of posts on persistent red-black trees, so you can look at his implementation there as well. So, okay. Yep, good, we've got time for this section. Now, what I'm going to talk about here is something that's it's in standard C++, in C++ 17. It's coming. There is a version already in Boost, has been for some time. Wondering if you can guess what I'm talking about. It's standard optional. So standard optional is very useful because it allows us to be more expressive in the intent of what we're doing with values that may or may not be present. And typically, we've represented these in the past by using pointers, where we're conflating pointed to something with whether it's there or not. Tony Hoare's billion-dollar mistake. Or we use sentinel values, such as integers that are not in our range. They're all a bit messy, they all have problems, some cases very expensive ones. So optionals just give us a way of encapsulating all of that and making the problems more or less go away, making it much safer to deal with values that may or may not be there, which turn out to be quite often as it happens, once you look for them. The problem is, well, first of all, let's just look at an example. Very simple one, an optional int, that we can just test whether we have one or not. And if so, we can use it. So much like using a pointer. A couple little advantages. It's more expressive. It's safer in that if we accidentally try to unwrap one when it's empty, it will give us a meaningful exception. But it's still not that safe because it's still quite easy to do that. It doesn't actually look a lot safer than just using a pointer. But there is one other method that the standard version and the Boost version have that can help. The method called value OR. So this gives us what in other languages you might call the coalescing operator. So it just says if we have a value, then use that. If not, use this default. So that's useful. It captures some common use cases. Problem is, it's not general enough. So that value may be expensive to compute. You may not want to do it eagerly. You may want to do it only when you actually need to. So it's easy enough to just write a little helper function to do the same thing. So here's value OR as a function that takes a lambda. Taking it as a template argument, you could put a static assert or something in there to just verify that it matches the signature. So this should be a lambda that returns the same type. And now we can use it. Well, the example here, I'm not really taking advantage of it. Still just returning a constant. But we've opened the door to lambdas. So you could put anything in there now. Make that as complex as you like and as expensive as you like, because it'll only get called if we don't have the value. So that's nice. And I don't know why they didn't put that in the standard, but there you are. But now we've opened the door to lambdas, we do something else that will solve our other problem. or at least go some way towards it. We can do it the other way around. We can have a lambda that's called only if we do have a value. So I've called this with, there's other names for it. So here's the first example. We're just going to call this lambda if we actually hold an integer. So you can see the integer being passed in unwrapped, so without the optional. And we don't need to check it and then unwrap it. We're given it, it's given to us in an unwrapped state. So that's immediately safer. We can't let the code drift due to refactorings or something, so it becomes unsafe because it's always enclosed within the scope of the lambda. So maybe a small improvement, but think back to what we were saying earlier about expressions versus statements. And here, we've made this, we've given it statement semantics, forcing us to use a side effect. So it's fine for standard cout, but we can't use this like an expression. And the reason is because of that if statement in there. We've only got the one branch. We've got no return value from the function. So let's see what we can do there. So we could do this. We could give it a return value of the same type. That now forces the lambda to return one of those values or an optional one of those values. And now we can treat it like an expression. So we're actually returning. That's going to be an optional integer, that j variable. And that's nice. There's one other thing we can do, though. We don't necessarily want to return the same type. A little bit more work, we can get it to return any type. So that little bit of boilerplate at the top is just sort of a type of trait that we can use to mean that our lambda can return over an optional value or a non-optional value, and it will add the optionality. And we're using decal type to extract the return value from the lambda. So apart from that, that should be fairly straightforward. And that means now we can write type converters in there. So here we're converting to a string, bit of a roundabout route, but that should do the job. And because we are now returning optionals, we can do something else. We can actually chain them. We can take the output of one call to with and then pump it into another call to with and do something else with it. So that's a nice property, but it's not very readable. And the fact is, C++ sucks when it comes to functional composition. A real functional language has ways of effectively inverting this flow so that you can nicely pipe the output of one function into the inputs of another. It's a very common pattern. And we can do it, but it's ugly and not really something I would recommend. Now, we can't solve that in the general case, as far as I know. We can do something a little bit more specific. If we rename a function into an overloaded infix operator, in this case I'm using the pipe operator to mirror Unix shell pipes. And with that one little change, the code transforms into something actually quite nice. I mean, yeah, it's still C++ lambda syntax, but you can read it, and you can see what's going on. We've got a pipeline here that actually scales quite nicely. Let's add a few more. We've got our type conversion in there now as well, at the end. And what's this on the second line? We've got a filter. That's really interesting, because now we're saying after applying the first lambda, if our result is 10 or less, we're going to return an empty optional. We'll effectively skip the rest of this safely. If we do have a value, we'll carry on and do the rest. So we haven't had to write any explicit logic to handle this changing of optionality, changing of types. We just glue these things together like Lego. And that's really what functional composition is and should be. In fact, there's another thing that's nice about this, is this pattern is very general. In fact, apart from that optional return, there's nothing in here that says anything about optionality at all. You could easily imagine writing the same pipeline for other things that we could write a with or a pipeline operator for, like containers, or async returns like futures, or there's lots of other things. Parsers can be written this way as well. In fact, this is so general that there is a very well-known name for this, or at least for what this is part of, because there's a little bit more to it. You're probably guessing that this is really the core of what we call the monad. Things that have properties that allow you to do this are monads. And what we've done is we've made standard optional, or boost optional, the maybe monad, named after the maybe type class in Haskell, which achieves the same thing. So that's the monad. And remember I said earlier that the standard algorithms weren't general enough, or they had some limitations. You can't do this with those. But the equivalent functional versions, you can. And in fact, I don't know if you've seen Eric Niebler's ranges talk. If you haven't, you really should check it out. It'll be in the references. It's one of the slides from his talk where he gives the final version of this solution he'd been working on throughout the talk. And you can see like a very similar pipeline here. Now he's written the functions separately, so we've just got the names in here. But it's basically doing the same thing. And he's effectively rewriting the STL, all of the algorithms, to work with ranges so that you can use them in this way. And with a couple of extra things, you can legitimately call them monads. Here's the output of that, by the way, if you haven't seen the talk. Just piping those things together actually produces a calendar on standard out. Interesting thing is, and this is the beauty of this, things like, for example, that chunk 3, group the months that belong side by side. If you change that number, it would change the layout. It's the only thing you have to change. Each part of this just composes nicely. It does its thing, and then just changes on to the next thing. And it just fits together. That really is the essence of functional programming. Just composing blocks into something bigger and useful while being able to reason at the block level. So I think it's a good time to bring up a quote from Kevin Henney. He did a talk, Functional C++. About 4 minutes in, he says this. Just let you read that and think about what you might want to drink this evening. Just a recap of what we've talked about. So we started off talking about the importance of expressions, what expression-oriented programming might look like, and some hints at how we might do that. The importance of local reasoning, of course immutability, but also how we can actually achieve that in practice. Some hints there, including builder types, persistent data structures, and we even finished by looking at how we can write monads. So, with that, I'd like to say thanks for listening. The quality of references and other talks that you can have a look at. So I've put them up on my website, levelofindirection.com, which you can also get to from extralevelofindirection.com, /storage/fcpprefs.html, or you can find me on Twitter. So thanks for listening. I think we have a few minutes for questions. My hearing is not great today, so you might have to shout a bit if you've got any. Or there's a mic, in fact. Yeah.
So you touched on it briefly in the first few slides where you said that, that person struct was more about the data that was needed and less about the, all the functions that come with it. I guess my question is kind of how much does this lead towards data-oriented design or data-oriented programming instead of object-oriented?
Yeah, I think there's a big overlap. Sort of coming from different places, but as often happens, things coming from different places tend to converge on something similar. I don't know enough about the specifics of the domain, but everything I hear about it makes me think of functional programming. So yeah, we're sort of looking at things from the same approach. In functional programming, you typically start writing your system by defining the domain types, just sort of abstractly as data types. And then you think about what you want to operate on those. So like I say, there's a different way of thinking to OO, and much more like data-driven design.
What do you want to see in C++ to support this style more?
So what do I want in C++ to support?
Yeah.
my biggest ask would be ranges, because they support a lot of this stuff out of the box. There's a really interesting interchange between Eric Niebler and Bartosz Milewski, I mentioned. They must have this sort of blog post shootout in a very friendly way, because Bartosz comes from more of a pure functional background, and Eric Niebler from C++, but a sort of meeting in the middle. So in the course of Eric's work on ranges, he's built more and more understanding of functional approaches, particularly monads, into the library. So that's going to be a big win, because that gets us some of the real benefits. I think it's too late to introduce immutability by default, but that would have been nice. Maybe a simpler lambda syntax. We're still getting improvements there. But I think, I didn't really talk about it here, but pattern matching is another big thing in functional programming. We're starting to get little bits of that dripping through. So C++ 17 has the structured bindings, just like a cut-down version of pattern matching. I'd like to see more of that, and there are proposals. So that's probably the biggest one that we might actually see.
Yeah, I have a question regarding the builder pattern.
Sorry?
The builder pattern.
The builder pattern, yes.
If I had an employee struct and I would leave the members mutable, I'll get two types out of the box, a mutable employee and a const employee. What are the limits of this design? Why did you choose to have a dedicated mutable type and not the one generated, the const type, by the compiler to avoid boilerplate?
So if I understand the question correctly, you're saying that if I just had my struct with the immutable fields, I can have a const version of that and get the benefits of the immutable type for free. The problem is that you can easily use that in a non-const way, and then you lose any constraints on the values between fields. What you would normally use, excuse me, normally use encapsulation for. You sort of lose control of that. If you make them const within the struct, then you know when you get one of these, you're guaranteed that this has been constructed once, and we're just seeing the same data being passed around. Might seem like a little thing, and you can shortcut it the way you're saying, at least as a starting point. There's other advantages. Once you separate the construction phase from the actual usage, for a start, you can often just strip out all of the methods or make them very minimal. Makes it a much lighter weight type to deal with, and just put all of the stuff to do with mutability and building and constraints and things into the builder. So you get a nice sort of separation of concerns there. And you may even use different types. So you may have types that are more appropriate while you're building things up. For example, you might have string builders in there. But then when you produce the final built type, you would use an immutable string. So there's a certain point where the wins are smaller, and you might choose to do it your way. But I think you very quickly scale out into cases where it's really nice to keep those very separate. Okay. Any more? Yep.
This may sound like slightly heretical, but don't you just end up having a lot of copies of stuff with different values floating around because you can't change the values? The direction I'm heading with that, because you said reasoning about the code, which I find attractive, but I guess maybe just in these very short samples, it's hard to get a feeling for how you would prefer to have a tree with half of it copied again, and being worried that someone's going to having this kind of monstered out, multi-dimensional data structure, which was already complicated to begin with. So could you elucidate that a bit?
Yeah, so I think there's two questions in there, really. First one, well, they're both good questions. The first part, if I got you right, is don't we end up with just lots of copies of things unnecessarily? And I sort of skipped over that a bit, but in usage, what you would do is, say you've got a set implemented using a persistent red-black tree. Then you'd have the set, and you'd say, right, add this node to the set. Now, internally, it will create this new red-black tree where most of the structure is shared. And only when that's completely done will it just swap the pointers over. And then the old one you probably don't need anymore, so it releases its reference. And now you've only got one again. So you don't necessarily even see that, but it happens safely. There's never this sort of in-between stage. Now, if you externalize that, you can make use of that, particularly with concurrency, where you can hold that in a shared location, and you can construct your new set off to the side where no other threads can see it. And when you're done, it's only a single atomic operation to effectively commit that into the location where you were holding the pointer to the previous one. Let's say that there's possibly a race where someone else does the same thing, in which case you might have to redo those operations, so you do it in a loop. That's exactly what we did, and most of the time we didn't get any contention. You have to allow for your use case, but it's just a very easy way to achieve concurrency quite safely that way. And again, makes it easier to reason about. And I've forgotten the second part of your question. Oh, the complexity involved. With the red-black tree, it did add a lot of extra complexity because of the rebalancing, which of course I conveniently didn't cover here. Definitely achievable. And that's why I mentioned the hash tree, because making it persistent is actually much more low cost. It's almost trivial to do. So there's not really much extra complexity involved. Does that answer your questions?
Yeah.
Yeah, great.
I would like to ask about cache meshes. And
About what, sorry?
Cache meshes.
Cache misses, yes.
Yeah, if this approach bring some kind of impact on it.
So, as I said, with the singly linked list, that's terrible for cache lines, cache locality. So I wouldn't recommend that where that's an issue. With the trees, can be less so. The hash tree also has the advantage of being more cache friendly because you can lay out these chunks very close together in memory. Can't remember the details of why that becomes more cache friendly, but I remember when I was implementing one before that's the way it works out. So in general, that's a pretty good bet. One thing I was going to talk about, but I cut it because I thought it was going to take too long. I started off talking about arrays and how they have problems, but you can achieve something like an array if you're prepared to accept a little bit of non-contiguousness, usually called a rope, and you implement it as like a tree, but where each node is a segment of an array. Usually, it's going to be some multiple of your cache line. So you get most of the benefits of cache locality with occasional hops, which then mean that the copying cost is mitigated. So you get sort of best of both worlds to some extent. And again, it's fairly easy to make persistent that way. They're also very popular for things where you hold large strings like text editors, because you can mutate things here without affecting the rest of it. So that might be another thing to look at.
The time is over. Thank you.
Okay. You can always find me at the JetBrains booth afterwards if you've got more questions. Thank you very much.